areas in the plane, or what's often called area between curves. So if you remember, the integral is the area under the curve, right? And the area here is a positive. Areas below the axes turn into negatives. And the area in between them, probably find an easier example to illustrate this on the next page. No, this is an easier example. If I want to find the area between these two curves, bounded by 0 and pi over 4, the area under this first curve is all of this in red, right? The area under the second curve is this part here. The area between them is the first one minus the second one. Or the integral of that makes sense so far. And we get this lovely definition that puts these two together into one thing. Because with integrals, we can separate pluses or minuses in separate integrals or put them back together. And the beautiful part about this is this even applies in this case, where they're not the same. Because, so for this little section here, oh, come on, I want upper minus lower, correct? Well, for that section there, I actually want upper plus lower, right? But the beautiful thing about it is minus a negative is a plus. So because this integral is negative, upper minus lower ends up being upper area plus lower area. And this last case, I'd want lower minus upper, which that's negative, minus a negative is plus. So the areas, this formula works as long as the things don't cross. Does that make sense?
Yeah.
So applying it to this one, I set up my integral like I did before. I integrate secant squared, I get tangent x. I integrate sine x, I get negative cosine x. So minus sine x becomes plus cosine x. It's it's minus negative cosine x. You plug in pi over 4. Tangent of pi over 4 is 1. Plus cosine of pi over 4 is square root of 2 over 2. Minus tangent of 0 is 0. Cosine of 0 is 1. The minus distributes through. That cancels. That makes sense. So this one, the first step here is finding where these intersect. Sure, you could graph them and find the intersection. You can also set them equal, and that's a parabola, right? It's, let's move everything this way. So plus x squared. So x equals -1 and 2. The upper curve has to be on top. So it does have to be upper minus lower. I would probably have just plugged that into the graphing calculator, but it was a pretty easy one to integrate by hand anyways. That makes sense. You are absolutely allowed to plug things into your graphing calculator. This one. Just be aware that you don't get it though for the CEI final. So for your course final, so you need to make sure you still know how to integrate. So maybe do something like half and half or something. So this is something I can integrate. Some of them will be terrible to integrate. Okay, finding the area between these two. Okay, the question is which one's on top? The x squared minus 1. So here's my two, y equals x squared minus 1 and y equals 2 cosine x. Which one of those is my top curve? No, that's my bottom. X squared minus 1 is a parabola shifted down 1.
Oh,
2 cosine x. Cosine x would go through 1, 0. 2 cosine x goes through 2, 0. So that's my top one. Um, Finding these intersections, let's just go ahead and do it with the calculator. So we're gonna do this whole thing with the calculator. And I'm gonna do this in a document just so I can use stuff. Actually, I should say 2 times cosine x. Sometimes it gets confused when I don't. And you do need parentheses. Yeah, that makes sense to me now as I think about it. Um, so I need to find my intersection point, right? Intersections 1.265. My guess is that they're just opposites, but it's easy enough to double check that I should. So now I'm going to do integral from negative 1.265 to 1.265 of upper 1 to cosine x minus a lot of times when I'm doing this, I'll use brackets around the big thing just to separate out so I don't do double parentheses. Doesn't mean anything more than a parentheses. Now I'm going to show you how I'm going to shortcut this when I enter it. I entered my 2 cosine x as f1x, didn't I? Since it's already on the graph, 4.99. And that's the guy. That's not so bad, is it? Okay. So this one. This is a little bit of an interesting one because if I want the areas, I should do the areas of them separately. So this right here, so I'm going to subdivide my section. This first part is simply that. The second part is this, because the square root of x is the upper curve. The lower curve is x minus 2. That just being a pretty simple line. Another thing I could do is this is a triangle, right? This triangle has area 1/2, base of 2, height of 2. I could have done this. Minus the area of the triangle, which is 2. The idea of splitting the region is important because sometimes your bottom won't be a triangle. But you can use geometric figures if they are. If your thing is nice, solid geometric figures, you don't need to do integrals. Okay. You can, if you're doing it on your calculator, it wasn't really that hard, was it? But you do need to know that you sometimes will have to split the region, and there is problems in your homework that you do. Okay. Sometimes we want to integrate with respect to y, which means my equation needs to be in x equals form. Okay. Upper is actually this side, lower is that side, because you're thinking about positive x's. Okay. This could be done doing it with y. Your upper being, you take this, when you solve it for x, you get that. You take this, when you solve it for x, you get this. So now upper minus lower is, and 10/3 was what you got for a result the other way too. You will have to sometimes practice doing some of these on y's. This one, it didn't really matter, did it? The other way was not that hard. I probably would do it the other way because I just think more in terms of x. But this one, some of these you might not be able to switch the functions. That makes sense. And especially when you have boundaries of things in y, the only way to do this is to do it in terms of y. The actual calculus doesn't change, but you have to think upper minus lower a little differently, and you have to convert them to x equals. A lot of cases they'll give them to you as x equals. Okay. So looking at this, do you think I should do this as x equals or y equals? So these are the two functions. You could do it as x and do this as upper minus lower and split it there. And then take this and just multiply it by 2. I think this is actually easier to do in terms of y. Because if you do it upper minus lower and you probably saw in the last one these little slices they're putting in.
Yeah.
Okay. That horizontal slice, and that's going to show up when we do volumes next week. Okay. So this is going to be x equals cube root of y. So upper comes cube root of y. I guess, so I'm going to have to graph this on the calculator to find the intersections. I don't know what they are. But it's going to be cube root of y minus y squared minus 2. This, however, to graph it on the graphing calculator, there it is. We'll need both of the plus and the minus. So we're going to have to graph 3 things.
But his pouch came from the line. Or I think that is what happened. Having board ones. And yeah, because I said so much and she got. So it's just the boom there. She got that books that she wow, but like she.
Okay. So now I've got all 3 of them graphed.
So, you can go.
Menu, analyze graph. So I actually have to select which 2 graphs I'm looking for the intersection on now. Oh, that one's just, -1. That's a nice value. So now I can do my integral. And the beautiful part with your calculator is it doesn't care whether you're integrating, whether your variable's x or y. As long as you're... I did pick the y coordinate, didn't I? No, I picked the wrong coordinate for my upper bound. I need to pick the y coordinate, not the x, because I'm integrating with respect to y. Does that make sense? For the other coordinate, they're both the same, so it doesn't really matter. but I always need to be picking the y coordinate. I guess I'm going to do this as y to the 1/3. I meant to hit cube root, but I hit the wrong button. And I get an area of 4.21. Does that make sense? And that's the area between curves. This isn't actually that bad, is it? I will give you reasonable. I changed the numbers on the final so that they're reasonable. Like, it's not an easy problem, not a super easy problem, but at least, yeah, it's at least much more doable than what came originally. So that is area between curves.